Hello again, my name is William Pye, and in this video we will be considering argument reformulation and proof strategy. Using the logical equivalences previously discussed, some arguments can be rewritten into equivalent forms, which can point to how a proof might be approached. Several arguments can be reformulated into different equivalent statements. In so doing, a method of proof can become more apparent and feasible. Below are some arguments discussed here. The merging or splitting of implications with the same hypothesis, what one might call a product, proof by contradiction, the laws of importation and exportation, proof by cases, and proof by contraposition. Examples of each will be given as they are discussed, with the notable exception of proof by contradiction. Proof by contradiction will actually be set aside for later use. If two implications have the same hypothesis, then the conclusions can be merged with the conjunction. That is, if P implies Q and P implies R, P implies Q conjunction P implies R, then I can rewrite the two implications as negation of hypothesis disjunction conclusion. For the first one, that gives me negation of P disjunction with Q. For the second one, that gives me negation of P disjunction with R. But notice, in both groupings, I have negation of P disjunction involved, with a conjunction in the middle. This looks like the result of the distributive law, which is reversible as an equivalence. For lack of a better term, I can factor the negation of P off like so, giving me negation of P disjunction Q conjunction R. But this too can be rewritten back as an implication. P implies Q conjunction R, giving me the equivalence. P implies Q conjunction P implies R is equivalent to P implies Q conjunction R. Now, if one views the implication as a unique morphism, this behavior is similar to the categorical notion of a product, which is the term I'm going to be using going forward. As an example, let's consider this implication. If the glass vase falls, then it will shatter and spill its contents onto the floor. Let's represent the sentences above with the following symbols. The hypothesis, the glass vase falls, will be represented by P. The first conclusion, it will shatter, will be represented by Q. The vase will shatter. The second conclusion, will spill its contents onto the floor, will be represented by R. The vase will spill its contents onto the floor. Thus, the implication can be symbolized by P implies Q conjunction R, which, as we've seen, is equivalent to P implies Q conjunction P implies R. So, to show the truth of this implication, all one has to do is actually show the two individual implications are true. That is, one needs to show that if the glass vase falls, then it will shatter, and if the glass vase falls, then it will spill its contents onto the floor. The following implication allows easier access to proving negations. So let's consider P implies Q conjunction negation Q. Rewriting the implication, I can rewrite that as negation P disjunction with Q conjunction negation Q. But Q conjunction negation Q is a contradiction. It's always false. So I can rewrite this as negation of P disjunction with false. But disjunction with false doesn't affect anything. That's the identity property, giving me negation of P. So P implies Q conjunction negation Q is equivalent to negating the hypothesis, negation of P. So, using the product property that we demonstrated above, this equivalence can be rewritten as P implies Q conjunction P implies negation Q is equivalent to negation P. Or, as an argument, you could state it this way. The first premise is P implies Q, the second premise is P implies negation Q, and the conclusion is negation P, that is, negation of the common hypothesis. Due to the conclusion being a contradiction, the argument is often called reductio ad absurdum, or the law of absurdity. As a proof method, the law of absurdity is often called proof by contradiction. At the beginning of this video, I stated I would not be presenting an example of proof by contradiction, so let me elaborate on why. Simple examples of proof by contradiction often seem contrived, in the sense that the result can be obtained by other means, say by modus tollens, disjunctive syllogism, or some other combination of inferences. A favorite example of proof by contradiction that I enjoy, proving the square root of 2 is irrational, requires mathematics to already be established. Considering a goal of this channel is to build mathematics from logic, it would break the flow of the series to jump forward to topics we have not yet developed. Likewise, some more interesting examples of proof by contradiction utilize quantifiers, which we also have not yet considered. Again, putting such an example here would break the flow of the series. Therefore, I will be withholding examples of proof by contradiction for their own video. If you would like, please leave suggestions for examples you would like to see in the comments below, and I will consider them for the episode on proof by contradiction, or a future episode. Speaking of negations, how does one prove the negation of an implication? Recall, an implication is false when the hypothesis is true and the conclusion is false. In fact, demonstrating this situation is a way to disprove an implication. The argument goes like this. The first premise is P. The second premise is negation Q. Therefore, one concludes that negation P implies Q must be true. So, how does one prove that this argument is valid? Well, here's how I would prove it. First, I invoke the first premise, P. By litotes, I can rewrite this as negation P. I now invoke the second premise, negation Q. By adjunction with lines 2 and 3, I get negation P conjunction with negation Q must be true. But since I have negations on top of a conjunction, I can pull those off at the cost of changing conjunction to disjunction with De Morgan's law. And I'm almost there. All I need to do is rewrite this as an implication. So I invoke the restatement of the implication, that is, P implies Q is equivalent to negation P disjunction with Q. By modus tollens with lines 5 and 6, I therefore get negation of P implies Q must be true, validating the argument. Consider disproving the following implication. If the room is illuminated, then the lamp is lit. Let's represent the sentences above with the following symbols. The hypothesis will be P, the room is illuminated. The conclusion, Q, will be the lamp is lit. Thus, the implication can be symbolized as P implies Q. Hence, to show the falsehood of the implication, I need to show that P is true and negation Q is also true. That is, I need to show that the room is illuminated and the lamp is not lit. Sadly, unlike implications sharing the same hypothesis, implications sharing the same conclusion cannot be joined with a conjunction the same way. So let's consider P implies R and Q implies R with conjunction in between. And I want to compare that to P conjunction with Q implies R. Let's consider the case when P is true, Q is false, and R is false. P implies R will be false, but Q implies R will be true. Conjunction these two and one gets a false statement, so this side happens to be false. On the other hand, if you take P and Q in conjunction them, you get false, but false implies false will be true. So this side is false, this side is true, so sadly the equivalence is false. Now, also, the implication is not associative as an operator. So what I want to do is compare P implies Q and that implying R. I want to compare that to P implies the implication, Q implies R. So comparing these two, well, let's consider the case when P is false, Q is true, and R is false. Let's see what happens there. Well, P implies Q happens to be true. But then take true implies false and you get a false statement. So this side happens to be false. On the other hand, you have Q implies R will be a false statement. But false implies false is true. So you have false on this side, true on this side, which gets me that the equivalence is false again. So now, these two failures are actually deeply related with the following equivalence. Let's start again with P conjunction with Q implies R. I can rewrite this as negation of hypothesis, disjunction, conclusion. But I can now use De Morgan's laws to distribute the negation, changing the conjunction to disjunction, giving me negation of P, disjunction, negation Q, disjunction with R. Now, disjunction is associative, so I can rewrite this as negation Q, disjunction R grouped together with negation P sitting outside. Now, negation Q, disjunction with R can be rewritten as the implication, Q implies R. But so can negation of P disjunction. I can rewrite that as implication also, giving me P implies the implication, Q implies R. So here is my equivalence. P conjunction with Q implies R is equivalent to P implies the implication, Q implies R. Now, the two directions of this biconditional are the law of exportation and the law of importation, respectively. And they resemble the categorical notions of a right adjoint and a left adjoint, respectively. To illustrate how this equivalence might be used, let's consider this example. Under the presumption that the printer is receiving power, if the power button is pressed, then the printer will function. Let's represent the sentences above with the following symbols. The underlying assumption, the printer is receiving power, will be statement P. The secondary hypothesis here, the power button is pressed, we'll call that Q. And the conclusion, the printer will function, that will be statement R. So the original sentence up here can be symbolized by P implies the implication, Q implies R. But as we've seen, this is equivalent to P conjunction with Q implies R. So, if you want to show the truth of the original implication, the original sentence at the top, then one need only show that the second implication is true. That is, one needs to show that if the printer is receiving power and the power button is pressed, then the printer will function. On the other hand, the conjunction of two implications with the same conclusion can merge. But De Morgan's law acts on the hypotheses, changing the conjunction into a disjunction. So let's consider again. P implies R, conjunction Q implies R. Let's rewrite those implications. The first one would become negation of P disjunction with R. The second one would become negation of Q disjunction with R. But notice this time, the disjunction with R in common. So undoing the distributive law, if you like factoring, I can rewrite this as negation of P, conjunction negation Q, disjunction with R. But what happens here is I have the negations, and I can pull that negation off, but De Morgan's law would cause the conjunction to become disjunction. So I now have negation of hypothesis, disjunction conclusion, giving me that P disjunction Q implies R. So here's the equivalence. P implies R, conjunction Q implies R, is equivalent to P disjunction with Q implies R. Now, if one views the implication as a unique morphism, this behavior parallels the categorical notion of a coproduct rather than a product. And as a proof method, the use of this equivalence yields what we call proof by cases. As an example, let's consider this implication. If the customer pays by cash or by credit card, then they can take the product. Let's represent the sentences in the following way. The first hypothesis, the customer pays by cash, will be statement P. The second hypothesis, the customer pays by credit card, will be statement Q. And the conclusion, they can take the product, will be the statement R. Now, the implication we have up here is P disjunction with Q implies R. Now, we know now that this is actually equivalent to P implies R conjunction Q implies R. So to show the truth of the original sentence, the original implication, all I need to do now is show the truth of the two individual implications, that is, the two cases. That is, I need to show that if the customer pays by cash, then they can take the product, and also, if the customer pays by credit card, then they can take the product also. Previously, the conjunction was shown to preserve implications. That is, if P implies Q, then one has that P conjunction with R implies Q conjunction with R. Unfortunately, the negation doesn't do the same thing. Let's consider P implies Q and negation P implies negation Q. In this case specifically, when P is false and Q is true. Well, false implies true is a true statement. But if you negate these, you get true and true implies false is a false statement, and true does not imply false, meaning this is a false implication. Doesn't work this way. Instead, the negation reverses the implication in the following way. Let's consider again P implies Q. Let's rewrite this as negation P disjunction with Q. Now, disjunction is commutative, so I can rearrange this, put in the Q forward. By the Litotes law, I can rewrite Q as negation negation Q. But this gives me a new hypothesis. Negation of new hypothesis, negation Q, disjunction new conclusion, negation P, giving me that negation Q implies negation P. Now, if one views the implication as a unique morphism, this behavior parallels the categorical notion of an involution. Moreover, this reformulation of the implication is what's called the contrapositive of the original implication. As an example of the contrapositive, let's consider this implication. If the room is not illuminated, then the lamp is not lit. Let's represent these sentences with the following symbols. I'm going to take the hypothesis without the not to be P, the room is illuminated. Likewise, let's take the conclusion without the not to be Q, the lamp is lit. So the original sentence, the original implication would be negation P implies negation Q. But as we've seen, this is equivalent to Q implies P. So if one wants to show the truth of the original sentence, the original implication, all one has to do is show the truth of the second implication, Q implies P. That is, if the lamp is lit, then the room is illuminated. And that's where we'll stop for today. Next time we'll introduce predicates and terms in preparation for quantifiers. Below is a list of references for today's video. We have Discrete Mathematics and its Applications by Rosen and Introduction to Logic by Suppes. If you like today's video, go ahead and hit the like button below. If you have a comment or question, go ahead and leave that below as well, and we will respond to you as soon as we can. Thank you for your time, and we'll see you next time. See you then.